Thank you, Philippe, and thank you for the invitation. This is my first extended stay in Belgium. And in fact, I worked very closely with somebody who was on the faculty here until about 1995, Michel Deville. He went from here to EPFL in Lausanne, and we were close collaborators. We wrote a book together also with Ernst Moon, who's another Belgian. So yes, this is in some sense a talk that is a continuation of my PhD, and you could argue, gee, didn't you like expand at all? You're just on the same track. And in fact, I expanded before I started my PhD. I started my PhD at Stanford, and they were doing spectral methods at the time, but in a box. And I said, I want to do something that's not in a box. And I thought, well, could you do a spectral element method? I asked Bob Mosier, we were office mates at NASA Ames at the time, and he goes, well, there's some crazy guy at MIT who's doing that. And I said, okay. And so I left Stanford. I worked for a few years, and I went to MIT, and I got to do my PhD with the crazy guy, and I never looked back. At the time, just to kind of put this into historical context, I have some historical numbers as I go through here, but at the time when I joined there, the world's fastest computer was the Cray 1S, which was 10 megaflops. And then there was the Cray XMP, which came out, which was 30. What was the difference between the XMP and the 1S? The XMP had 3 paths to memory, 2 in, 1 out, instead of just 1. So you tripled without changing the CPU too much, just tripling the bandwidth. So 30 megaflops. And by the time I finished my PhD, we were hitting 40 megaflops on, and I don't remember if it was 128 cores or 32. We had access to both. And those, kind of another interesting historical point is that particular machine, it started out with Intel 286 processors, then switched to 386 processors. These numbers we'll see in a little while. But they had attached vector hardware. They had attached graphics units. And so we've actually been doing accelerated computing since the late 80s. I was writing special graphics card code. I spent a lot of time at Intel learning how to do that to get our performance up. So this is kind of, this is a nice example of the types of things that we're interested in. This calculation was done by Alex Obapko at Argonne. It's a configuration that was brought to our attention by a physician who had a patent on this device. And what this is, it's a vascular access device for people who are doing dialysis. So this needle is stuck into the arm, into an artery, into a vein. And the idea is to take, actually for this particular device, usually it goes from artery to vein. Okay, so high pressure to low pressure, clean blood, you go through the hemodialysis, you come back into the vein. I do not know which vessel he planned to stick this into, but this one would take the blood up the outside annulus and then bring back the clean blood that has gone through the hemodialysis machine and inject it, I think, into the vein because it's heading towards the heart. And if you look in here, you can occasionally see fast-moving flow moving in the annulus up towards the machine, and which is not modeled here. And then the idea is that there's a hole right about here where the blood goes up and then it comes out, and you don't want the two to mix. That was the question that he was trying to address with these simulations. Fortunately for us, he found somebody who would build the mesh for about $2,000, but actually quite a good deal, as many of you might know. And it was one of the founders of TrueGrid, which is one of the, we have all hex meshes, so that's a challenge for us. So here's another calculation. This is done by the group at ETH Zurich. They've since done, they're interested in combustion. They've also since lit this thing off. But this is compressed turbulence. So this is a low Mach number calculation. And you can see the heat flux here at the top dead center of the compression stroke. And so one of the questions that I was always curious about, and again, this comes from the Stanford days. Bill Reynolds had a sapphire cylinder that they were using lasers to measure, what does turbulence look like under compressed flow? He said, we don't even know what it looks like. And that was one question that stuck with me forever. finally, 5-10 years ago, we were able to look at and solve this problem. And of course, when I tell you the answer, for those of you who are fluid dynamicists, it will strike you as obvious. But the turbulence scales really go up at top dead center, and then they fall away as you expand. And one way to look at it is the Reynolds number goes up because the density goes up. That's the easiest way to look at it. Another way to think about it is you're under isotropic compression. You have a vortex, and you pull your arms in, you spin faster. This is kind of our bread and butter stuff. We work a lot with Ilya Marzari and about 10 or 15 nuclear engineers in the nuclear engineering division at Argonne. They are heavy users of our code. This calculation was done on a machine called Polaris at Argonne, which has 2400. Oh, no, this is a B100. This is probably done on Summit, not the A100. And clearly it's a turbulent flow in a 17-rod bundle with wire wrap to keep the pins separated, and a blockage. And so they want to know what happens with these blockages. How rapidly would these fuel rods heat up if they don't get the coolant going through them. So some statistics about this. It's 36,000 steps in a 6-hour run, 60 hours on 10% of Summit. The pressure takes about 85% of the runtime. That's the stiffest part of these calculations for incompressible Navier-Stokes. And it's inescapable. Okay, why is it inescapable? Well, think about it this way. If you have flow in a pipe, and it's incompressible, and you push on this end, the flow everywhere accelerates to the speed that you've pushed it in a single time step. What that means is that every processor has to know somebody is pushing on the pipe. It's global communication. It's inescapable. Okay, it's not quite inescapable because the physics really doesn't go at infinitely fast. It's the mathematical model that does that. It's a very efficient mathematical model. Physically, what happens is there's an acoustic wave, right? Pop, 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 pop. But we don't want to wait for that acoustic wave to propagate down. You could do that, but that would be very slow. Okay, so it's really coming from the mathematical model. I'll be talking about the solvers tomorrow for people who care about that stuff. But there are a couple of interesting points over here. 480 V100s and a half a second per time step. Why not 960 V100s and get to half the time? That's the question, and I'll talk about that throughout the talk. There are 27,000 V100s on Summit. They are available, and you are encouraged to use more of them. You generally, on these big machines, get shorter queue times if you ask for, unless you ask for the whole machine, but larger jobs get higher priority. So we'll talk exactly about that question throughout the talk. That's what I call the user's perspective. The user cares about, it's 60 hours of run. That's several days, especially when you count the queue time. Why not get it done in 30 hours, right? Or in 10 hours? We really care about that. Okay, so this is our equation. And this divergence-free constraint that I was talking about is why we have this global coupling. So that's really the principle. The bottom line is we are communication intensive. You can't escape that. So that's really, we do some math, and that's the important takeaway here. Okay. So what about scalability? So the Exascale challenge. So let's put up a model for scalability. Let's talk about the speed. We can call it in gigaflops, teraflops, whatever you want. If you're running on P processors and Eta is the parallel efficiency, and suppose Eta is 1, and suppose you get 1 teraflop per GPU, let's say, which is not an unrealistic number. If you run on 100, you should be getting 100 teraflops. Okay. The problem is Eta, of course, and this is just the definition of Eta. So this is inescapable. You measure this number, you measure these numbers, and then Eta is just the ratio of those two. Okay. So the whole idea is to keep Eta from going to 0 as P is increased. All right. And so what controls that is the scalability of the application. The code, ideally the code doesn't matter. If we all collaborate amongst ourselves, which is part of our C project, we really collaborate, make sure nobody's, because if somebody's 10 times faster, you're gonna say, what are they doing? What am I doing wrong? And you fix your code. That was one of the objectives going into this project, because we brought together lots of people of a like mind to push this technology forward. The platform matters and the size of the problem matters. What really matters, as it turns out, is the size of the problem divided by the number of processors. Okay, so we should be able to get this p-fold speed up. Why not? We should be able to go to 1 million. Why not? I actually have a separate talk where I've analyzed that for several iterative solvers. I decided to not cover that today. But before, even before there was Blue Gene Q, people at IBM were arguing, oh, you'll never go to 1 million processors. And I was there with Rusty Lusk and a bunch of people from Argonne. We're all looking at each other, why not? Right? And we could see no barrier to doing so. And so Rusty and several of the scientists at Argonne in the group that Tomal was working with wrote this paper, why not? Going towards 1 million processors, why not? We went back to IBM, same conference room 2-3 years later after Blue Gene Q was running with 1 million processors. And the guy stands up and goes, well, nobody will go to 1 billion processors. And everybody looked at me because I really objected when they said it the first time. But so I was at an ECP NASA meeting last year out at Ames. A lot of their codes are running on thousands of CPUs. They have weeks to months of runtime. And they kind of were asking the question, should we go to GPUs? What should we do? And so we've brought everybody together for that. But the point is weeks to months of runtime. That's the class of problems that we're talking about here. Okay, so here's some strong scaling results. This was in our first paper from the ECP project, the C project. This was figure 1, in fact. And so, here are 2 strong scaling plots. And this is on Blue Gene Q. Blue Gene Q. So here we go. We double the number of processors. We go down by a factor of 2. Double again, another factor of 2. So 2, 4, 8, 16. And then we fall off a little bit. And so either you're going to stop here or you're going to stop here. But let's talk about what you're probably not going to do. So this is the user's perspective. The user's probably not going to run out here because they know, oh, I'm doubling and I'm not getting any further real gain. So I'm burning my core hours without benefit. They're also very unlikely to run here because it's 16 times slower. Why wait 16 days when I could wait 1 day, right? What about energy consumption? Guess what? This one is just as energy efficient as this one, right? Because I'm using 16 times as many resources for 1/16 of the time. There's no energy penalty if you can strong scale, all right? So it's a very important consideration because, when you have a 20 megawatt computer in the computer room, people really care about energy. They want to design for lower energy consumption. Kind of an interesting data point. Now, we have these exascale machines, and people are thinking, okay, is that a scale? All right, well, if we're at 50 megawatts, now we're talking 50 gigawatts. Whoops. So it puts the pressure on how you have to reduce the power consumption by a factor of 100 at least to make that even a tenable concept. So really, it pushes some very good computer science questions. Okay, so time to solution goes down with increasing P, particularly when eta is 1, meaning we're on this dashed line. Now over here, we can see we can drive out to far, more processors than we could here. Out here we can use 8192 instead of 2048. And all that we've done is we've changed the problem size. And so in fact, if you rescale this to put number of points per rank, in other words, the problem size divided by P, these 2 curves collapse. So which is why I argue that N over P is the important parameter here for assessing scalability. And in an ideal world, what you'd like to do is push this value of N over P down, 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 down. Okay, and you would also like to increase your speed as long as you don't bump up the N over P. Okay, so what's the root cause of the fall off, and can we do something about it? So same 2 curves, same data, just now replotted. Here's parallel efficiency. We get the usual little cache bump here, and then we fall down. And then here's throughput, number of gigadots per second or dots per second versus N over P. So obviously these 2 curves are just the same with a change in the y-axis. We'll be looking at a lot of plots like this, but you can think of them as parallel efficiency plots in some sense. And what we want to know is, okay, where do I cross, let's say, the 80% parallel efficiency mark? So which would be the 80% of we usually take the saturated value as the peak value. Really, we should take the peak value, but we don't do that. On GPUs, we rarely see that cache bump. Okay. So this was our first paper, and we looked at this for several bake-off problems. And the idea was we did, instead of classic strong scaling, we just fixed the number of processors for that paper, 16384 on Blue Gene. We could always get access to that. That was on the small machine, because the big machine had 800,000 cores. And then we did these runs. Everybody, all the team members did these runs. And we just make the problem, we vary the problem size and look for where we had this fall off. Okay, and so this became, for the our whole C project, this was the general figure of merit, DOFs versus number of points per rank. And so we call that N scaling. You know, this P is fixed, and it's not exactly weak scaling, it's more like strong scaling. Okay, and so here are some of the results from that paper. So participants were us, NEC 5000, Zanio Kolev and company at Livermore, the MFM team, and then Martin Kronbichler and the DL2 team. And so really it's just Martin. And Martin has done a lot of optimizations for modern CPUs, by the way. Probably best performing high order codes that I know of are the stuff that Martin's doing. Now he obviously is doing something very clever in threading, but once he starts strong scaling, boop, it falls off, because he was simultaneously using 8 threads. The way he'd written it, he had not anticipated pushing N over P to that small a value. Okay. So several takeaways here. First of all, we all learned from Martin, like, wow, there's some things we could do. And then he also, I think, came to appreciate that, you know, strong scaling in these kinds of environments is quite important for the reasons I already laid out. All right. So when we did this study, when we looked for the 80% parallel efficiency, we took from the fastest of the 3 codes. It's not fair to compare 80% of a slow code. You take the fastest out of the ensemble, and then you compare everything against that. And from that, you can generate what we call the T sub 0.8. How long does it take to solve the problem if you're at 80% of the peak realizable? So clearly we have 3 codes. This is the peak realizable here, and out of our ensemble. Okay, and it turns out for each of the bake-off problems, there was always a different winner. So it's not like one team won for every case. And the whole idea going into it, again, as I asserted before, was you want to be the loser, because for free, you can figure out how to make your code faster. You're already happy with your code, but now you know how to make it faster because somebody else is doing that. Okay, so and keep in mind, when we started this project, we knew that the ECP was going to be building GPU-based exascale machines. I don't want to imply that all exascale machines have to be GPU-based. It's just that the DOE was targeting that, and that's why they were funding us to make GPU-ready codes. All right, but at the time, we were all CPU people. And so big questions were, okay, well, so let's look at the time to solution. That's what the user cares about. And if you double the amount of work per grid point, it's going to take twice as long as you fix the N sub 0.8. If the speed goes up by a factor of 10, it will take 1/10 the time, but not if N sub 0.8 goes up. So you can imagine a scenario where somebody comes up to you and says, hey, I've got this new CPU, it's 10 times faster. And you go, great. They go, problem is you need 100 times as many grid points per CPU. My time to solution just went up by a factor of 10. That's really bad. And that's what we thought we might be getting into with GPUs. We did not know where we're going to end up at the end of the day. So we cannot let this ratio increase. That's all that matters for time to solution. It's not the speed, it's this ratio that matters, all right? And so, you know, clearly though, you do want to maximize S sub 1. And then the question is what happens to N sub 0.8? So we wanted an all-in approach, and that was driven by our earlier experiences on the Titan machine at Oak Ridge, which had NVIDIA K20s. This was work done by Misun Min and her team in 2014. So here's GPU results on Titan, here's CPU results on Titan, and this is Vesta, which is kind of a GPU. And so the granularity limit here is where we have one spectral element of degree 14 here, okay, per MPI rank, okay. And you know, you can't subdivide, that's the atomic unit, you cannot subdivide. And so it takes, you know, maybe 20 seconds on Vesta, which had relatively slow CPUs. It's faster on Titan. And then we have here the GPU. This is P equal 1, 2, 4, 8. But even on just one GPU, we suddenly encountered something I had not thought about when we started looking at that in 2014, which was, we run out of steam on the GPU. And it just shows that I was not very familiar with their architecture. But it does start to slow down. And so this is the 80% mark right here, this line. So it says for the GPU, we need about 100,000 points. In fact, over here, we only need a couple thousand. But the GPU ultimately is still faster than the CPU in this case, right? But now if we go to polynomial degree 7, which is what people are more likely to use, in fact, the Titan CPU is faster than running on the GPU. So now there's some interesting questions. One is, I already argued that coming down here on this blue line is equal in energy consumption. So there's no penalty for this point on this blue line. So we're at 1, 2, 4, 8, 16, probably 64 cores. I don't know how many they had per CPU. And then this GPU, in fact, I think this would be faster to run this problem on the CPUs on Titan per node than to use the GPU. That was bad, right? Where's the incentive to convert to the GPU? It's going to run slower. And by the way, this is highly tuned code. We worked closely with the OLCF and with the NVIDIA people. So this is good, well-performing code. It's just it was not a well-designed machine. That they put too much CPU power on it with respect to the amount of GPU. On Summit, we get similar results, but you have to use a lot more cores to be faster. And in that case, you're not wisely using your resources. It turns out from an energy perspective on Summit, it was better in power by a factor of 10. Okay. Just to get back to the question of CPU scalability, here's BlueGene Q. You can definitely scale this out to 1 million ranks. This machine also raised interesting questions early on, because for each core you could run 1 rank, 2 ranks, or 4. 4 wasn't so good, so I'm only showing 1 and 2 here. And the 1 rank one, the red, strong scales better than the green one. So which number should you present for strong scaling results? And the answer is, well, how's the user going to use the machine? They're going to use the green curve, right? Clearly, they're going to use the green curve because it runs faster. So you do that, and we hit the 80% mark at about 4,000 points per rank on BlueGene. Okay. So we always follow this practice when we present our metrics. So here's an example. This is Frontier and Crusher. These are MI250Xs. These are AMD products. Again, 3 different problem sizes. If we convert to number of grid points per rank, we get the curve collapse. We have 80% parallel efficiency here at about 2.8 million points per rank. Okay. So that's a pretty good figure of merit for GPUs, current GPUs, is somewhere between 2 and 5 million points per rank to hit this 80%. And it also seems to be quite universal across other codes. I've measured it for other codes. Everybody's in that ballpark, even for time explicit compressible codes. Okay, so what's causing this fall off? On CPUs, it's really MPI latency effects, and it's not bandwidth. Anybody know why it's not bandwidth? It's because out here, I have 4,000 points per rank. So I have this little cube that's 20 by 20 by 20. My message size is 400 words. That's a latency dominated message. It's not a bandwidth constrained message. Okay, that's what's killing you. By the time you get to the point where bandwidth matters, it doesn't matter because you have so much work. It dominates all the communication. So what really kills us here is latency, not bandwidth. We really care about latency, and most of the latency comes from the software stack. And I blame Thomas for that. I always rail on it's good to have a friend in the MPI group go, hey, come on, you guys, you're killing me. So, yeah, so that's, on CPUs, we have that. On GPUs, the problem's twice. We have this GPU scalability that we saw with that blue curve, and when you get down there, you could also have MPI latency and even potentially bandwidth effects, because now you have not 4,000 points, you have 2 million, and the surface area is larger, and you might be affected by bandwidth, okay? So it's a completely different scenario. Okay, so just a little bit of historical stuff. I've been tracking this stuff forever. here are ping pong tests on the Intel Delta, which is i860-based machine out of Caltech. 512 is the world's fastest machine in 1991, and other machines. And so what we see is that the ping pong latency time as a function of message size has come down over decades, all right? But when you rescale them by the clock rate, which is all that really matters for us, they become more tightly coupled. And so here's the data from 1986 out to 2021. This is summit on the bottom. This is the rate. This is the inverse flop rate. Okay, so I mentioned the IPSC 286. We could get 50. It was 50 microseconds to do a flop, and then when you added the vector accelerator, it was 0.33. On the 386, it was 10 microseconds to do a flop, and the accelerator speeded up a little bit to 0.25, and so on and so forth. But look over here with the impact on so here's the measured latency on this. Now on this chip, the latency is gated by the CPU, which is running quite slowly, all right? So when we accelerated it, going from the 286 to the 386, the latency time came down by that ratio roughly, actually in this case, factor 6, all right? But the relative latency, when you added the accelerator, was huge, right? 18,000 versus 120. And now down here, 3,700 versus 93. It's not that these numbers are good or bad, it's just that they're different, okay? And you make different design choices accordingly. Here's the relative latency for Summit. Okay, its real latency is 0.0005, many orders of magnitude faster than sorry, this is the real latency here, 2.5 versus 6,000. But its relative latency is just absolutely huge. So you want to think twice about sending a message, but you have to do it. Okay, so what are the mitigation strategies? Well, one is you just have to add more work, right? So you can you're not dominated by communication. So you increase n sub 0.8. You can also cover communication with computation. You can have multiple messages in flight, and then you can make algorithmic changes. Let's talk about covering computation with communication. On BlueGene, you can't do that, right? If you only have one element, there's nobody to be doing work while you're waiting for that message. But if you have 2 million or 8,000 elements per rank, these are high order elements, there are enough on the surface, you can do those, send them out, and then you can do the rest, okay? But if you have a small number, there's no gain to be had. So that's one change. Okay, what about latency mitigation strategies for CPUs? BlueGene was lovely. It was repeatable to 3 digits, day in, day out, month in, month out. And it was because they had a low noise network. Every network was convex. When you asked for your chunk of BlueGene, it was a cube. Everybody had a cube. It's not that you have a cube that's important, it's that everybody else has a cube. Nobody is surrounding you and sending all their data traffic through your subnet. So super clean. It also had support for hardware all reduce. We don't cover communication computation, as I mentioned. We looked at a lot of these issues, an effort led by Ken Raffinetti at Argonne. They chose this title, I didn't, but the title was "Why is MPI so slow?" As a SC, it was SC17 paper. And Ken gave a very nice talk about what they could do, and in particular, what they could do to reduce latency. So that paper does look at those issues. So one of the other things that they did on BlueGene was they had 18 cores per node, 16 were for compute, 1 was for system stuff, and then 1 was for yield. Okay, so you could at least improve your chances of getting a good die. Here's the all reduce time. It's very respectable. For a one-word all reduce for a dot product, for example, it's 100 microseconds. Sorry, 10 to the minus 4. Here's the hardware all reduce. For processor counts going from 16 up to 500,000. Hardware all reduce is just 4 times half the round trip ping pong time. In other words, I send you a message, you send back, I divide that time by half. If I do an all reduce on the entire machine, it's 4 times that value, independent of P. Fantastic, okay? You don't have this log P scaling, so there's no reason you couldn't go to 1 billion with this architecture. From this perspective, there might be from power perspectives or cost. And just so comparison, here's Frontier. Ping pong is the dark blue here. Sorry. Ping pong is the green. So the ping pong ping pong on Frontier, which is in red, is better than the ping pong on Mira. Okay, so they've reduced the latency. That's actually good. They have much faster CPUs, by the way, than Mira. All reduced. Mira crushes. Even the software Mira was here at 1e-4. This is up at 2 or 3e-4 for the all reduced. Right? And we care about all reduced because optimal algorithms require projection. Right? If you don't have that projection, you're not finding the best fit in the search space for iterative methods. It's very important. It's so important that there must be 250 papers out there about people trying to rewrite conjugate gradients so they can reduce the number of all reduces. It could be done in hardware here, and then those arguments are spurious. I mean, you don't need that. Okay? It's really critical. So it turns out we discovered while we were developing a fast coarse grid solver, again, we'll talk about that tomorrow, that our fast coarse grid solver was as fast as all reduce on Frontier. How's that possible? Because it's also an all-to-all. And so I just pulled out some F77 code that I've had since 1986 or 88. Actually originated with Intel, and boom, it was faster to do that all reduce than it was the MPI. And so Ken invited me to come and get shouted at by the people at the MPI booth at supercomputing. It was fun. Tom was there. One of the points they made was, well, maybe you can tweak your environment variables. I'm like, no. It's a basic operation. If I'm going to do that, I'm just going to use my own code. Right? Why would I don't have to tweak anything if I can write source code that outperforms it. Okay, so what about getting S1 to be super fast? Again, think back to 2017, we had no GPU code at least for our Navier-Stokes solver. But I've known Tim since he was a graduate student in the 90s, and we've been working together for 4 or 5 years before that, and we signed him up for this project. And he has a long history of writing high performance code for high order methods on GPUs. And he's developed a lot of tools. One of the tools he's developed is Akka. And so people who wonder about the maintainability of Akka, well, Tim's quite committed, I think, here, because it's on his license plate. And so I knew that if we follow this path, we can leverage all the work that Tim has done. And at the end of the day, we'll have performance. That was the big question. Like, we have to jump in, all in. We want to absolutely make sure it comes out. We have to performance. So Akka is a front-end language. You write these kernels, and then they get converted into CUDA, HIP, OpenCL, or DPC++. Graduate students are able to write the back end, so if we need something else, a graduate student can write that. So that's the approach we took. I'm not going to go through the Akka code per se, but I will tell you, let's look at this graduate student thing. When ChatGPT came out, I said, hey, can you write an Akka kernel for a Saxby? Sure, here you go, blah, 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 here it is. Cool, it knows Akka, right? And I kind of forgot about it, didn't do anything with it. But then I was in a position where I really needed something. And I realized that wasn't the right question. The right question is, so NecRS is our GPU-based version. But I go, can you write a routine for me that does this for NecRS? Goes, well, based on the version I have, it would look like this. And the nice thing is there preserved all of the stylistic approaches that were used in NecRS. It wasn't vanilla Akka code, it was vanilla NecRS code that obeyed the stylistic things that had been built into the language. And it was just brilliant. I go, well, can you give me the kernel for it? Because it originally wrote the C++ code. And it goes, okay, the Akka kernel would look like this. And about 20 minutes and 5 iterations, I was up and running. I had my piece of code that stabilized that particular calculation. And I said, this is just great. I can fire all the experts. No, I don't have to bother our heavily overloaded team of one who's doing most of our development. That's Stefan Berkelmeyer, who's right. So I suddenly felt, okay, I felt a lot more comfortable about the whole thing. So what about the performance that this thing can deliver? Well, these are A100 numbers, and then throughout the project, new hardware kept coming out, and we're very interested in the MI250X because Frontier was using it, and El Capitan is going to use the MI300. And we had this strange behavior, our kernels for the, this is for the fast diagonalization method. So we basically are doing this tensor contraction. We go, here's the right-hand side, we go into wave space on each little spectral element. So it's a local block solve. So these are the matrix of eigenvectors, and we do this contraction. It's an orthonormal matrix, so we're getting the inverse here. And then we divide through by the diagonal, the eigenvalues, which would be like k squared plus L squared plus M squared in Fourier. And then you do your Fourier transform, your generalized Fourier transform back to physical space, a linear combination of the eigenvectors. Okay, but these are really nice tensor contractions. Here they are, A100. That's getting about 4,700, so 4.7 teraflops. And this is FP32 because it's part of the preconditioner, so we only have to do it in 32 bit. But we weren't getting good numbers for the MI250X, so Tim Warburton spent a weekend, and here are the new numbers for the MI250X, and he cleaned up this even odd problem that we had, and got this up to 5 teraflops, which was beating the A100, but the exact same code also boosted the A100, it turned out. So this kernel is running, in FP32 about, we run it typically with 10. Well, let me rephrase it. Polynomial degree 7, and it's additive Schwartz, it gets out to 9. So we're running here at about 7 teraflops, FP32 on the A100. The log file prints out all of the performance, and we select out of all the kernels that have been written, we select the fastest one at runtime. So here you can see that for this fast diagonalization method, it picked the 7.4 teraflops and the 4.31 for the smaller polynomial, because P multigrid. Here are the convection kernels. These are FP64, they're a bit lower. This is on Perlmutter using SS10. Hang Wang at NVIDIA wrote some Akka code for us. He was obviously a very good CUDA programmer, but he could understand Akka. And he boosted the advection kernel from, on the A100 from 4.7 to 6.3 T-flops. And for the H100, an impressive 12 T-flops, although we don't have any H100s. I think there are a couple machines in Europe that are going to have H100s at Barcelona, and I'm not sure where the other one is. So we don't need just Tim Warburton. Other people can write these codes. Peng also took care of this one. This is just the matrix vector product. It's in FP64. Different polynomial orders and at different performances. So I just want to point out a couple of things here. So the V1 is faster on the A100. Let's just stick with that. But if you're running polynomial degree 10, V1 would not be faster. But since we picked the fastest kernel at setup, there would be no performance regression here. It would find that V0 was faster than V1. All right. It's really a good idea to do that. And on the first, actually it's a pre-processing step before the first time step. It tests all the kernels and picks the fastest one for each one. We do the same thing on the communication. We have lots of different communication patterns. So some possible communication patterns on the GPU is you could pack the buffers on the GPU, then send them via GPU direct to another GPU. Or you could pack them on the GPU, push them through the CPU. Or you could just send it to the CPU and have it do the packing and the send. And the choice depends on the size of the message and the interconnect topology and everything else. So we can see here it does that. All of the P multigrid levels, except for the coarsest grid, it finds that pairwise plus is the fastest for that. And you can see here the different bandwidths that we're realizing. This might be an old slide where I have a slightly off value on the actual bandwidth. The relative values are correct. But what we notice is that when we go to SS11, the bandwidth went up by the advertised factor of 1.5 over SS10. So Slingshot 10 versus Slingshot 11 on Perlmutter. All of the main machines are using currently SS11. That really gave us pause at that time 2 summers ago. Oh, I'll get to that in a second. Right? Finish one other thing. So a couple other improvements. So we overlap communication computation, about a 15% gain in the pressure solve time. FP32 in the preconditioner, 10 to 15. We might be higher than that because we now have more of it in FP32. Curiously enough, the FP32 had really evil consequences with the Slingshot 11. So this is the purple here is Slingshot 10 in 2022. And then let's see, should be green, so these X's here are Slingshot 11, just 1 day later. At this processor count, the Navier-Stokes solution time is factor 3 higher. We traced it back to this kind of the coarsest kernel in the multigrid, where you're sending very short messages of length 32-bit each. And they were taking 100 to 1,000 times longer, such that the overall Navier-Stokes time went up by a factor 3. This was devastating for us, and it was extremely repeatable. You can see there are multiple curves here. These are strong scale studies. And it took them about a year. They finally got it fixed to here, SS11, and now it's actually faster than SS10. And notice that it's faster where bandwidth matters. It's not that much faster where bandwidth doesn't matter, which is exactly what you would expect. So we were delighted to get that fixed because since all the other machines were going to be Slingshot 11. Okay, so it's kind of starting to summarize some of the things here. We have A100 performance. We're hitting about almost a teraflop, full Navier-Stokes on multiple processors. The n sub a half here is around 5 million grid points. And here, the n sub a half on Frontier is around 3 million. So in fact, Frontier is going to run faster than Polaris at the strong scale limit, right? And that's a legitimate, real, observable speed up. You could argue, well, I could go way out here and hit this teraflop, but nobody would do that. You'd run 2.4 times longer. Okay, so here are a number of, these are strong scale, are this like the earlier plots, but I wanted to break down some of the things that are going on Frontier. This is the advection kernel, which is not communication intensive at all. Frontier is quite slow. Now, this is even after, I think even after we did the fix. And then Frontier is also, no, I take it back, I'm sorry. Summit is quite slow. Frontier is just as fast as the A100, okay, for the advection kernel. But the coarse grid solve time, which is for Crusher here in black, is significantly slower than Perlmutter. So the network is not as good on Frontier and Crusher. This is one of my favorite questions. Somebody walks in and says, hey, how long is it going to take to run my problem? Right? And first you have to ask them what the problem is. And here's my favorite exchange with a student. How big's the problem? Oh, I don't know. It's 1 billion. No, it's not. It's 10. No, it's not 10. And you have to walk them down to get them to pick a value, right? Because you have to have a value before you can do anything. And so you walk them down and squeeze them. And so, but here's one where the problem is well defined. This is a CPU problem run by the KTH group, Philip Schroeder. They were running on one of the local KTH machines. I can't remember it's probably a Cray. 3.2 billion grid points, 35 million CPU hours were used, blah, blah, blah. Very nice DNS, or Cord Reynolds number 400,000. So, how many A100s would this take? That's an important question if you're going to go out and buy a machine. All right, and how many node hours? Well, we just take the numbers we know. First of all, what are we going to do? We're going to run at 3 million points per A100, right? Bang, now I know how many A100s I need. We also know what the time per time step is going to be. And that's going to be 0.3 seconds per time step. I know that already because I've done extensive timings. We know what the T sub 0.8 is. It's going to be between 0.3 and 0.5 seconds time step. And so from that, you can back out how long it's going to take, 110 wall clock hours. Each A100 is 300x times one of these CPUs, blah, blah, blah. So you can answer that question, right? From just looking at the type of analysis that we've already done. Okay, so here are the n sub 0.8s on the V100, about 2 million, about 3 million for a single GCD on MI250X. One thing you have to be a little careful in this business is AMD sells something they call a GPU. It has 2 GPUs on it, right? And I say, our GPU is faster than the A100, but nobody would use it as a single GPU. They all run it as 2 MPI ranks. So it's really, from our modeling perspective, it's 2 MPI ranks, it's 2 GPUs, okay? Same thing with Intel point of vecchio, PVC, 2 tiles. Okay, so it's 2 GPUs. So that's the comparison. We're comparing, again, from the user perspective, how many ranks do I have? Rank to rank comparison. So for a single GCD, it's about 3 million per rank. And on the A100, about 4 to 5 million. Did we improve this n sub 0.8 versus S1? Okay, so here's a big run on Mira. We do not have too many calculations that overlap, all of Mira to let's say Summit or to modern machines. This was done by Ramesh Balakrishnan at Argonne. It's DNS low past the periodic Hillet, Reynolds number 19,000. It took about a half second per time step. We know the N over P is 2060. It's a little beyond our perfect strong scale limit. It's 24-hour run of several. And then the equivalent run, 528 ranks, again, at the correct N over P. This is on the V100s. And it's about 0.14 seconds per time step. So we're a factor 3 faster. Okay, that's a little weird. The GPU is 300 times faster than the CPU. So how do you assess what's at this strong scale limit? That's where everything happens. Okay, and so then at the end of the day, yes, we got a gain. We did not go backwards, which is what we were really afraid of doing. That's why we invested in Tim Warburg. We wanted to make sure we didn't go backwards. Okay. Okay, here's another calculation. 99 million spectral elements, polynomial degree 8, actually. It's 350,000 pebbles in a bed. 50 billion grid points. We ran on all of Summit. About 1.4 terabytes per snapshot, FP32. It's a very high quality all hex mesh generated by a Voronoi cell technique. About 300 elements per sphere. And when we started this, we were hitting like 0.68 seconds per time step, but through extensive tuning at this scale, we were able to get this down to about 0.24 seconds per time step. And we could actually double the time step size, go up to a CFL of 2, and get to effective time step of 0.18 seconds per time step. But the bottom line is we could do the entire flow through time in 6 hours. On Blue Gene P, it took many, many weeks to do flow through time through a smaller system. So this is really a big deal. Nuclear scientists can solve a single flow through time in less than a day. That's on Summit. Summit is small compared to Frontier and Aurora and El Capitan. It's about the third of the size. Record problem size on Mira was 15 million. This one was 98 million. And now we're running 1.6 billion elements. So we've gone up by a factor of 100 in problem size. We've only gone down by a factor of 3 in solution time. Okay, it hasn't gone up. Okay, and so this is one of the big runs. This is a full core model run on Frontier. It was coupled with neutronics, and this is running a billion elements. I'm going to show the fluid mechanics results. Here's the full domain with the turbulence. Hopefully the movie just let's see there. One of the little squares is a 17 by 17 rod bundle, 27,000 elements in the cross section. And there are 37 of these 37 of these assemblies. This is a small modular reactor. And you can see it's really turbulent everywhere. The ultimate goal is not to be doing turbulence everywhere. The ultimate goal is like do turbulence in DNS in one section and some kind of reduced order model or brands in the other. And we are doing that as well. Validating everything along the way. So our initial runs on Frontier, now we're running not at 1,000 nodes, we're running at 9,000 nodes, so 72,000 ranks. And bad news here. Sometimes it's taking 10 seconds of time step. Usually it's kind of what we expect, 0.3 seconds per time step. But and there's this big gap here. And so what this gap reminded me of is back in my early days visiting Intel, I was advised that if a message doesn't go through, it gets kicked back, and it can take 10 times as long for it to get through the system if you get this kickback. So you really want to make sure that the path is greased so messages can go through. And so I thought, well, okay, what happens is, maybe that's what we're having here. It's 10 going up by a factor of 10. There's nothing in between. It's either it works or it doesn't work. And we looked around, and really surprisingly, it was not in the pressure salt where we have the multi-grid. It was in the velocity salt, which is just Jacobi preconditioned conjugate gradients. It's just going bang, 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 putting messages out via GPU direct. And it was doing, the messages are 3 times longer because you can do all 3 velocity components at the same time. So more opportunity for congestion because you have longer messages on the in the queue. So we tried instead breaking it into 3 separate messages. That definitely improved the noise. We also explored turning off GPU direct. That was most effective. We had very few shots to debug this because only 1 out of 4 would run, and you sat in the queue for a very long time. You're asking for the whole machine. But these are the results if you turn off GPU direct. So it really made a big difference, right? And now we're sitting here at a very comfortable number, somewhere between 3 and 4, 0.3 and 4 seconds per time step, and hitting 28 petaflops total. Right now, on low processor counts on Frontier, we occasionally hit 750 gigaflops. So even this 390 value is a little bit low. We'd like to do more investigation. But so it is possible to sustain up to 750. Okay. Okay, a million times I tried to put this. I'm going to see if I can get this. Yeah, let's do it this way. So progress towards exascale. People are observing a 3-fold increase of the strong scale limit, 1.15 per second per step. Huge problems, billions of elements versus tens of millions of elements. Portable performance through Okta, sustaining almost a teraflop per A100. A quote from Ilya Marzari, who I understand was here earlier this year or in the fall. Once the students switch to the GPU variant, they never go back. It's really palpable. I mean, it does run fast. You're like, oh, a couple of GPUs, it really makes you good. And these bake-offs were really good mechanism to increase productivity across the project. Okay, so that just keep in mind a teraflop. That was the #1 machine back when I joined Argonne in 1998. That was #1. That's teraflop. So let's see if I can get this to go down. Okay, so what might we do for the future? Well, obviously we'd like to increase strong scalability. How can we do it? As I mentioned before, 2 main issues with GPUs: reducing the kernel launch overhead and reducing message passing latency. And people will argue you can be half full or half empty. I'm kind of a half full guy. And fortunately, the kernel latency issue, it looks like there is a path forward. Somebody on the seed project took the BP1 and just as a single B100, no MPI, but he rewrote the entire conjugate gradient kernel or the solver into a single kernel. And yes, a 10-fold decrease in the n sub 0.8, which means you could run 10 times faster if you didn't have MPI overhead. Okay, and you even got a boost in the peak here. So it is possible to address this kernel launch overhead and reduce, to get away from the strong scale limiting factor of the GPU. And then for CPUs, convex subnetworks, to me it doesn't seem that hard. Obviously we're beggars, right? Not choosers, because we have to take whatever the industry is building at a reasonable cost. Hardware collectives, that actually, for BlueGene, that was dependent on having a convex subnetwork, but I'm not sure that's necessarily the case. And then one-sided message exchanges. Thomas came into my office a year and a half ago. He was so excited. I go, no, come on, nobody does one-sided. I'll pass you my data when it's ready and not before. But he convinced me, and he convinced me that indeed you could get lower latency if you do that. And anybody who mentions lower latency has my attention. And so we invited him to a meeting last fall, and he gave a very good talk. So that was quite exciting. So I'll stop there and thank you all for your attention.